Hello everybody and welcome to the video on section 16.5. This is the final video of the probability and statistics section. This is the final section of the probability chapter and the topic is measuring risk. So we're going to end the chapter with an application section. Probability is applied all over the place. It's an extremely applicable field. And so trying to quantify risk is one of the main areas in which it is used, and that's how we'll finish the chapter, by thinking about how can you apply probability to risk. In particular, in section 16.4, we defined the term expected value. In this section, we will apply this concept to gambling and to insurance premiums. So since expected value is itself a probabilistic idea, this section is essentially just applied probability. So in this video, I'm just going to show you two examples. They are both essentially contained inside your book, and this section is just, there's nothing new in it really. It's just an example-driven section, just applying expected value. So let's start with our first example. It's a game called Chuck-a-Luck. It's not terribly popular anymore, although you can still find it at carnivals. If you walk into a casino, you won't find it. It used to be more popular. But anyway, you'll still run into it from time to time. Here are the rules. To play this game, you will hand over a $1 bet to the casino. You then roll 3 dice. If the 3 dice all come up 4s, then you get a profit of $3, and the casino hands you back your original bet, which gives you a total payoff of $4. Okay, so imagine in your head what's happening here. You are handing $1 over to the dealer, or whoever, the casino worker. If you roll 3 4s, he hands you $3 back in profit, plus your original bet back. So that's what this $4 here represents. $3 in profit, plus the dollar he's handing back to you that you handed him to begin with. If you roll 2 4s, you get $2 in profit, which means the casino will hand you back a total of $3, right? You hand them $1, they hand you that $1 back, plus an additional $2. If you roll 1 4, you get $1 in profit. If you roll no 4s, you just lose the dollar you bet. So there are basically 4 outcomes here. You can win in 3 ways, and each of those winning outcomes gives you a different profit value, or you can lose, and if you lose, you just lose your bet. The question is this a game you should play? If it is a game you should play, what kind of profits can you expect to make over time? And presumably, this is a yes or no question. Presumably the answer is yes if you can expect to profit over time. Presumably the answer is no if you can expect to lose over time. So if not, if this is a game you should not play, what kind of losses can you expect to sustain over time? So if you should play this, can you quantify what kind of winnings you should get? If you shouldn't play this game, can you quantify what kind of losses you should expect? There are 3 different ways you can win, as we've already pointed out, and 1 way you can lose. Therefore, there are 4 possible outcomes to this game. What is the probability of each outcome? We're going to spend some time computing these probabilities for the next few minutes. What's the probability of winning $3 in profit? This is the best outcome for you, obviously. It's the most money you can win. And equivalently, what is the probability of rolling 3 4s? Well, there are 6 to the 3rd equals 216 ways of rolling the 3 dice. So think of rolling 3 dice as rolling dice in stages. You roll dice 1, that's stage 1. You roll dice 2, that's stage 2. You roll dice 3, that's stage 3. So the multiplication rule says you just take 6 times 6 times 6, which is what 6 to the 3rd is. So there are 216 ways of rolling the dice. And again, you could start listing these out if you don't believe this number. It would just take a long time. Like you could do 111, 112, 113, 114, etc. And eventually you'd be writing things down like 343, 344, 345, 346, etc. it would take you a long time to write them all out. Okay, so there are 216 ways of rolling the dice. There is only one outcome in which you roll 3 fours. It's just 444, right? There is only one way you can win that $3 in profit. Therefore, the probability of winning this amount is 1 out of 216 possibilities, or 1 divided by 216. Let's now go to the opposite extreme. What is the probability of losing your bet? Which is equivalent to asking, what is the probability that you roll no fours? Well, how many ways can you roll no fours? If you think of each dice roll as a stage, like we just did a second ago, there are 5 options for each stage. Okay, so in stage 1, you can't roll a 4. In stage 2, you can't roll a 4. In stage 3, you can't roll a 4. Well, if you can't roll a 4, you can still roll anything else. You can roll a 1, 2, 3, 5, or 6. Therefore, at each stage, you have 5 options, and the multiplication rule says the total number of ways to do all 3 stages is just multiply the ways you can do each stage, which in this case is 5 times 5 times 5. And that number is 125. So again, you could list all possible ways of rolling 3 dice and getting no fours. You would write 111, 112, 113, and then you would not write 114 because you're not supposed to get any fours. So you would skip that and write 115, 116, and then you would keep going. If you did that, you would have 125 things written. Now, if you remember from 16.3, to calculate the probability of something, you take the number of things you're interested in, which in this case was 125 ways of rolling no fours. You take that number and divide by the total number of possibilities, which is 216. So in the first case here, we only had one thing we were interested in. There was only one way to roll 3 fours. Now we have 125 ways of rolling no fours. What is the probability of winning $2, which is rolling 2 fours? Okay, so we're halfway there. We've analyzed the probability of winning the most. We've analyzed the probability of winning the least. Now we have the 2 in-between cases. So the probability of winning $2 is equivalent to asking, what is the probability of rolling 2 fours? So let's think about that. There are basically 3 ways you can roll 2 fours. Die 1 can be a 4, die 2 can be a 4, followed by something that's not a 4. So 441, 442, 443, and then not 444, right? Because that's 3 fours, but 445 and 446. Or the first die can be a 4, the third die can be a 4, and the second die can be something else. Or the first die can be something else, the second and third dies can be 4s. So since x here can be any one of these 5 numbers, you can't fill in a 4 for x because you're only allowed to have 2 4s, but you can fill in anything else. We get 5 things from here, plus another 5 things from there, plus another 5 things from here, and that results in 15 total ways to roll 2 4s. Therefore, we have a probability of 15 out of 216. That's the probability of winning $2 in profit, or equivalently, the probability of rolling 2 fours. So we've now gotten 3 probabilities. We've gotten 1 over 216, 15 over 216, plus 125 over 216. So we've accounted for this much of the probability in the system. And so if you add these up, 125 plus 15, that's 140, and then plus another 1 is 141. We have accounted for 141 out of 216's worth of the probability. So what's left over is 75's worth of the 216. And therefore that must be the probability of rolling 1 4, because that's the only possibility that's left. Okay, so there are 4 total outcomes, right, as we said here. 3 different ways to win, and 1 way you can lose. We calculated the probability of winning the most. We then calculated the probability of losing the most, right, winning the least. So that was 2 outcomes down. Then we did the probability of winning the second most. And with those 3 numbers in place, we now know whatever is left over must be the probability of the last option. So here is a summation of everything we just did. And by the way, this example is in your book if you would like to read through all of this. You can roll 3 fours, 2 fours, 1 4, or no 4. If you roll 3 fours, the casino worker will hand you $4. He'll hand you $3 plus your original $1 that he was holding for you. If you roll 2 fours, the casino worker will hand you back $3. $2 in profit plus your $1 bet. If you roll 1 4, the casino worker will hand you $1 in profit plus your original $1 bet. If you roll no 4s, the casino worker hands you back nothing, right? Just keeps your dollar. So these are your payoff options, where again, by payoff, I literally mean the amount of money that the casino worker hands to you. So he'll either hand you $4, $3, $2, or no dollars. And here are the corresponding probabilities. Okay, once you have a table like this, just like in section 16.4, you can compute an expected value. And the way you do it is by just multiplying down and then adding. Multiply down, add, multiply down, add, multiply down. And if you do that, you get an expected payoff that looks like this. 4 times 1 over 216, right? Multiply down. Plus, 3 times 15 over 216. Plus 2 times 75 over 216. Plus the 0 payoff times 125 over 216. And if you add all that up, you get approximately 92 cents as your expected payoff. So what does that mean? Well, expected values tell you what happens in the long run. They tell you nothing about what happens in the short run. So in the long run here, what this literally means is that you should expect to lose about 8 cents per turn. So per round, you're going to lose about 8 cents. So in the long run, the average amount per turn that the casino will hand back to you is 92 cents. Since you hand over $1 per turn, right? You're handing them $1 and they're handing you 92 cents back. That's bad for you, right? This is a game you should not win, and therefore you should not play. So notice that we've learned a couple of things. Not only have we learned that this game is bad for you, we know exactly how bad it is for you. We know you should expect to lose about 8 cents per turn if you play this game for a long time. So just to illustrate this, I've written a computer program, so ignore all this. I've written a computer program that simulates playing Chuck-a-Luck. So the actual dice rolling is all in the background here, but what I will do is I will just tell it, I want to play 5 times. And then it gives me the data of what happened. Okay, so I rolled 0 4s, 3 of those 5, ooh, that's bad, 1 4 once, and 2 4s once. Okay, so the total amount of money I handed the casino during that process was $5. Okay, so I pay $1 every time, right? Every play I pay $1. The total amount of money the casino gave back to me was $5. So when you rolled this 1 4, they gave you $2 back. When you rolled 2 4s, they gave you $3 back. Therefore, the amount of money the casino gave back to you per turn is $1. So these $5 divided by these 5 turns, right? The amount of money I got divided by the number of times I played was $1. So let's do this again. So this is the expected payoff here. This just was the payoff here per turn. The total payoff was $5, but I played 5 times. So I didn't really make anything here. So how many times do I want to play? I'm going to play 5 times again. Wow, this actually went better for me. I won 3 times. It was the lowest win, but that's okay. So the total amount of money again was $5. This time the amount of money they gave back to me was $6. So that's good. The amount of money the casino gave back to me per turn was $1.20. So back up here, I basically won $0 per turn, right? I paid up $5, they gave me $5 back. Now I'm making a profit of 20 cents overall, right? So per turn, per turn I'm making a profit of 20 cents. So that worked out for me that time. Let's do this again. 5 times. Oh my goodness, I lost them all. So I handed the casino $5. The amount of money the casino gave back to me was $0. So therefore, of course, the amount of money per turn they give back to me is $0. Okay, so the key numbers here are $1 per turn they handed back to me, which was neutral for me, right? I mean, I neither made money nor lost money because I handed them 5. They gave me back 5. In this case, I got $1.2 back per turn, which was good for me, right? Anything above $1 is good for me because I'm handing them $1 every turn. And in this case, I got $0 per turn back. So that was bad for me. That was like the worst possible thing. Okay, so keep those 3 numbers in mind. 1, 1.2, and 0. Those numbers are kind of all over the place. Now I'm going to play Chuck-a-Luck 10,000 times. Okay, so I have a ton of time on my hands. I'm sitting at this table for weeks. I rolled 0-4s this many times. I'm not going to read these numbers to you, but here's the data. So since I played 10,000 times, the total amount I gave the casino was $10,000. The total amount of money the casino gave back to me, the computer just calculates all this, was $9,200 or so. Therefore, when I take this number and divide by the 10 grand I ponied up, the amount of money the casino gave back to me per turn was 92 cents. Okay, so let's do this again. 10,000 times. Notice that these numbers here are pretty close to these numbers here. 43 times versus 47 times. That's not very far off for winning it all. So in this case, the amount of money the casino gave back per turn is about 91 cents. So let's just do this one more time. 10,000 times. This worked out a little bit better for me overall. I handed them 10 grand. I got back 9,300 or so for a payback of 94 cents or so. And one more time. Okay, 90 cents or so. Okay, notice these numbers from playing lots and lots of times, right? 10,000 times is in the long run. That's a lot of times played. These numbers here, this 90 cents, 94 cents, right? 91 cents or so, 92 cents, these numbers are not all over the place. They are very close to each other, and in fact, they are very close to this number, right? This 92 cents that we got. By contrast, when I did things in the short run, so playing it only 5 times, that's in the short run, okay? That's not very much data. The amount they gave back per turn was kind of all over the place, right? $1 per turn, $1.2 per turn, $0 per turn, right? So there's a distance of $1.2 between these numbers. But down here, when I started doing things in the long run, things sort of leveled off and things were predictable now. The casino could expect to keep about 8 cents per turn from me, right? So among other things, this expected value analysis, this is why casinos stay in business. Casinos are in it for the long haul, aren't they? They are in business for, months upon years. So everything they do is in the long run. So in the short run, the casino has no idea how much money they're going to make from you or lose to you. They have no idea. If you sit down and play 5 roulette wheel spins or something, who knows what's going to happen, right? But in the long run, the casino knows exactly how much money they're going to make. And they just run an expected value analysis like this, and they'll know. So any casino that still plays Chuck-a-Luck, they'll make about 8 cents per person per round off of that game in the long run. Not necessarily in the short run, but again, all the casino cares about is long-run behavior. So here's one example of an application of expected value. We now have applied it to gambling, and we've given it a different name, but it's the same idea, expected payoff. So again, you hand the casino $1 per turn, they hand you back 92 cents per turn in the long run. That's bad for you. Let's now move on to our other example of insurance premiums. So the kind of insurance we're going to consider here are warranties. Okay, that's a kind of insurance. So consider this example. You own an electronics store and you sell LED TVs. For the sake of this toy example, let's assume the price is all the same for all of these TVs, 650 bucks. As an extra way to make money, you decide you're going to sell 3-year extended warranties on these TVs. You've been selling these TVs for a while, and from previous data, you know that 75% of your TVs will have no problem within this warranty time period. So 75% of those TVs require no attention. Okay, those are good for you, right? Because you just take the customer's money for the warranty and you don't have to do anything for the customer. On the other hand, you know that 20% of your TVs will require a repair costing $120 within the first 3 years. So these are bad for you because that means that if a customer buys the warranty, you are on the hook for that $120. Furthermore, you know that the remaining 5% of the TVs will have a problem so severe that they will need to be replaced within the first 3 years. So we have 3 outcomes here. Either a TV needs no repair, which is good for you. It will need a minor repair, let's say, costing $120, or they will have to be replaced, which, if you are the person selling this warranty, is the worst outcome for you. Okay, well, warranties cost something, don't they? And you're the one creating them. So here is a perfectly reasonable question you should ask. What price should you charge, right? Presumably, if you're selling these things, you're making a profit off of them. So what price should you charge if you'd like to make a profit of, let's say, $20 per warranty? The $20 here is arbitrary. Okay, you want to make some profit, so I filled in a number there just so that we could compute something, but this is the kind of question that, dealerships, stores, whoever, they have to make these computations all of the time. They're always answering this question when they're selling warranties. We know we want to make a profit of some set amount, so what price should we charge? Okay. So up front, we don't know what price we're going to charge, but we have to give it a name. So let me just call it P for price. So let's let P denote the price you're going to charge for your warranty. This table now shows everything we just described in the previous slide. There are 3 possible outcomes. The first outcome is that the TV is fine. Well, if the TV is fine, then this is the payoff to you, the owner of this store. The customer just hands you P dollars and you keep that P dollars. So let's just say P is 50 bucks, right? We don't know that yet, but let's say P is 50 bucks. If a customer buys a TV and they buy an extended warranty and their TV is fine, then they've just handed you 50 bucks and they get nothing from that 50 bucks, right? Except for peace of mind or whatever. But you don't have to do anything for them for that 50 bucks. On the other hand, the TV might require a minor repair. If the TV requires a minor repair, what is the payoff to you, the electronics store owner? The customer has handed you P dollars. So they've handed you like 50 bucks, right? So that went into your pocket. But now you're on the hook for that $120 repair. So the total payoff to you is a plus P, but then minus 120. So again, if P turns out to be 50 bucks, the customer has handed you 50 bucks, but now you have to pay 120 bucks. So the payoff to you is now negative 70. Same thing for TV replacement. If the TV has to be replaced, the customer has given you P dollars, right? But now you have to pony up the cost of replacing the TV, and that cost is 650 bucks. And these numbers were given in the problem also. There's a 75% chance the TV is fine, a 20% chance the TV needs a minor repair, and then a 5% chance the TV needs to be replaced. As always, though, once you have a table like this, you can compute an expected value, and you do it by just multiplying down, add over, multiply down, add, multiply down. So in this case, you get 0.75 times P, that's this column, then add this entire entry here, this P minus 120, all of that times 0.2, and then this entry here, P minus 650, all of that is multiplied by 5%. And so I don't know how long it's been since you've done things like this, but when you have a number times a parenthetical expression like this, you move the 0.2 to both values. So you do 0.2 times P and then 0.2 times negative 120. And that's where this comes from over here, 0.2 times P minus 24. So 0.2 times 120 is 24. And same thing here, 0.05 times P, that's where this comes from. And then you have to put the 0.05 also with the 650, which gives you now a negative 32.5. So as the owner of the store, as the seller of these warranties, your expected payoff is whatever price you charge minus $56.50. So just to be clear here, this first expression here was gotten by just multiplying down, add, multiplying down, add. These equal signs are just simplification. So 0.75p plus 0.2p, what's that? Well, that's 0.95p, right? You can just add the coefficients. And then plus another 0.05p, now you have 0.75 plus 0.2 plus 0.05, but that's just 1. Okay, so you can verify that. 0.75 plus 0.2 plus 0.05 is just 1. So that's why there's just a p right here. And then minus 24 minus 32.5, that is negative 56.5. Okay, so what does this mean for you? This means that whatever you charge, in the long run, you should expect to lose $56.5 from that charge, right? If I'm going to charge my customers P dollars for this warranty, I'm going to lose about $56.5 per warranty in the long run. Therefore, the price I charge should be bigger than $56.50, right? If I charge the customers $20 per warranty, my expected payoff will be 20 minus $56.5, which is negative $36.5. That would make no sense. That would mean you are losing $36.5 on every warranty you sell. You would not do that. What you'd like is to make a $20 profit per warranty. Okay, so all we need to do now is take our expected payoff and set it equal to 20, because $20 profit per warranty is what we want in the long run. So in the long run, this table will hold true. About 75% of the TVs will be okay, 20% need this minor repair, 5% need this replacement, that will hold to form. And so in the long run, everything will balance out, and we'll end up just charging people $76.50 for this warranty. Okay, so we need this expected payoff to be $20 per warranty. That's why this equation here is true. So if I wanted to make $10 profit per warranty in the long run, I would have put a 10 right here. Okay, so this might be a tough sell to your customers, right? They're already spending $650, and then you want to charge them an extra, basically $80 for this warranty. But if this data is what it is, right? What data was handed to us, wasn't it? This is the price you would need to charge if you want to make a $20 profit per warranty. Okay, so both of these examples, again, there's nothing new in this section. Both of these examples are just expected value, and now we've called the concept expected payoff. But it's the same thing. You create a table where now you have payoffs listed across. So in this case, we didn't know what the payoffs were yet because we didn't know what this P was. But in the Chuck-a-Luck example, here it is, we knew what the payoffs were. We didn't have to find the payoffs. We did need to find the probabilities, though. That took a little bit of work. But once you have a table where you have payoffs and then probabilities of those payoffs, to compute an expected value or expected payoff, you just multiply down, add, multiply down, add, multiply down, keep going until you're done, and that will be the expected payoff. And that will be the average amount per turn or per warranty, per whatever, that you will get in the long run. So in this case, if P is $76.50, then in the long run we'll make $20 per warranty. Back up here in Chuck-a-Luck, we handed $1 over and we got 92 cents back per turn in the long run, right? So on average, in the long run, we'll lose about 8 cents every time we play. Okay, so that is now the conclusion of chapter 16, and we've now looked at several applications of probability.